Hello, welcome back. We're going to cover decision trees now, because to understand what a random forest is and how it works, you need to understand how decision trees work. So imagine you have a data set with 1,000 examples in it, and what you're trying to do with this data set is predict the income of every person in this data set. So you have 1,000 people and 1,000 incomes, and what you also know about each person is you know their age, their gender, and their years of experience. So how can you use those three variables to predict income using a decision tree? Well, here's how it works. Let's draw it out. First of all, you have your variables. I'm going to list them up here. Okay, so we have listed income is what we're trying to predict, and we know the age, gender, and years of experience of everybody. Those are our X variables. So how it works is, and we have, remember we had n equals 1,000. So 1,000 observations in our data set. So what we start with is we start at the very top of our decision tree with 1,000 observations. That's what I wrote in there, 1,000 observations. Then what the decision tree does to build the branch of the decision tree is we look through each one of these X variables and we try to split the data. So first we say, hey, let's split the data on age. What are ways we could look at all of the people, all of the people in this data set, and what are all the possible ways we could split the data set based on age? So for example, you might say, hey, let's put to this side everybody whose age is less than 30 years old. And then this side would be everybody's whose age is greater than 30 years old. Then what we're doing is we're going to calculate, well, what's the average income in each of these buckets? Let's say the average income in this bucket is $100,000. Okay, so high income individuals. $100,000 income for all 1,000 people. But when you break it into age, what you find is people with less than 30, who are less than 30, let's say their average income is $50,000. 50,000. And people greater than 30, their average income is $150,000. Let's say in this data set you have the same number of people in each one of these splits. So by doing this, look at the difference between these two groups. You have 50,000 versus 150,000. So there's a $100,000 difference between those two groups. So by splitting on age, specifically at 30 years old, we get a very big difference between these two groups. We could have chosen a different split point. Maybe we split at age 35 instead of at age 30. By doing this, we see all of these can change. So it might not be 50,000 anymore, it might be 60,000. And it might not be 150,000, it might be 170,000. Now, and then these would change to these numbers, so you might have 600 people and you might have 400 people. But what we see is the gap between these is even greater. And in an actual decision tree, the quality of the split, so how good the split is, isn't measured on this raw gap number. It's actually measured in mean squared error. So you pretend you have a model, and for your model, you're just going to take everybody whose age is less than 35, and you predict that their income is $60,000. And then you take everybody whose age is greater than 35, and you predict that their income is $170,000. And then you find your mean squared error from that very simple model where you only have two predictions. Your goal is for each variable, so for the age variable, you find the split which has the largest mean squared error, or essentially, as a rule of thumb, the biggest difference between these two groups. Let's pretend that this is the biggest mean squared error for age. The next step in the decision tree is you go to your next variable, gender. Well, gender only has one split, male versus female. So let's say we were to erase age and only split on male versus female, and the difference between male and female is, let's say, 80,000 versus 110,000. That's the difference between those two groups. Well, that's a lot less than age, so what we do is we'd stick with age. We wouldn't change this to gender. Then we could go to years of experience. And let's say we try to split on years of experience, and we find that if somebody has 1 year of experience or less, they only make $50,000. And if they have more than 1 year of experience, they make $200,000. Let's make it really, really big numbers. Well, then the decision tree, this will be replaced with years of experience less than 1 year and years of experience greater than one year. What did I say this was? The difference? I think it was, we'll make up new numbers, doesn't really matter. We'll say the average for under 1 year of experience is 40,000 and above 1 year of experience was 200,000. And then there are n equals 100 people in this group, n equals 900 people in this group. And so by iterating through all of these variables, we find the single variable and the single split point, which leads to the highest difference between these two groups as measured by mean squared error. Or what you could think, again, is just the average income of both of these buckets. And then once you do that, you've done the first split. But now you have more splits you could do. And for each one of these nodes, you repeat the entire process again. You start at age, and you split this node on age, so people who have less than 1 year of experience, the 100 people in this bucket. What's the best split point for age? What's the best split point for gender? And what's the best split point for years of experience again? And you pick the best years of experience metric, or the best split point for these other variables. You do the same for this side. And once you've repeated that several times, you're done with your decision tree. So I'll draw a few more on here real quick so you can get an idea about how one will look. Okay, so what I've drawn is a few more possible split points. These might be the best split points following this node down. So what this is saying is people who have a year of education or year of experience greater than 1 year, greater than or equal to 1 year, and who are male would be expected to make 180,000. If they have both of these and are also their age is less than 25 years old, they would be expected to make 100,000 in this data set. If it's greater than 25 years old, they would be expected to make 250,000. And so what you could do, if you wanted to predict somebody, let's say somebody comes up to you that has 1 year of experience, who's male, who's over 25, well, how you would use this decision tree is you would say, well, let me see, let's follow it down. You're greater than 1 year of experience, you're male, and you're over 25. I would expect you'd make $250,000 a year. Now, these seem like really good jobs, okay? And I want to, whatever industry this is, this would be a good one to work in. But here is basically how a decision tree works. Of course, each one of these would continue branching out until you get to very small buckets at the very bottom. So here's the basics of what a decision tree is. Those are the steps to complete a decision tree. You could do them by hand, but it'd be incredibly laborious. Luckily, we have a computer do it for us nearly instantly, like we saw in that previous example. Now, before we move on to the next topic, I want to show you something really powerful and interesting about decision trees, namely their ability to model nonlinear relationships between variables automatically. And so for this, I'm going to ask Mike to come up here. Okay, before Mike comes up, we're going to look at a simple example, an example that a linear model could solve. So imagine you just have a very, very simple data set with one x variable and your y variable. And here's, when you plotted x versus y, this is sort of the line you get. Well, you couldn't just use standard linear regression to solve this equation because of this nonlinear relationship. if you were to use standard linear regression, you'd get this. Something like that, a line that goes through, and you could do better than that. So instead, we would include x, but we would also derive a variable. We'd make a feature, and we'd include x squared in our equation as well. By including both, we can then model this line, this nice curve. Now, what a decision tree would be a little different. Let me redraw this same curve. So what a decision tree would do is it would look at this and it'd say, how can I split this data in two ways so that both data sets are as different as possible? And so where it might split like this, just right down the middle, right here. And so whatever value of x this is right here would be the split point. Then what it would do is it'd look at these two chunks recursively and repeat the same thing, where it'd look at this chunk and go, how could I split this so that both sides, the average value of both sides, are as different as possible? And I'm going to write this, so this was the first split we did. This is your first split. Then it might do the split right here. I'll actually write the 1 here and the 2 here for clarity. So the second split could happen right here. And that means all of this stuff is different than this stuff in our decision tree. This part of the chart is different than this part. Over here, this sort of looks pretty much all the same. It's pretty close. The average value of this line segment is pretty much equal to the line segment itself. So it might not actually go any further there. But here, we can do better. So the decision tree might split here and split here for the third level. And so here's the third split. And so what you could almost imagine, this, you could view it upside down, in where this goes like this. This goes over here. So as the split points. And then we could do one more here. Then here's the final little buckets each one would land in. And so to see how the decision tree would approximate it, if this was the full decision tree, we would take the average value of each one of these little segments here, which I'm representing by this dotted line, and then this equation, this step equation, would be what is learned by the decision tree after only 1, 2, 3 splits. So it very efficiently starts learning this curve. And if you would do mini splits, so you'd keep on splitting these over and over again, you'd find it'd be a step function nearly on top of this line. And so without any work on your part, with just training a decision tree, it's able to recover the actual line from the data. So for this next example, we're going to take a more challenging line. This is a very simple line with a few splits, but I'm going to have Mike come up and draw a strange function. And we'll show you how a decision tree would handle it. Okay, Mike, here you go.
All right, here comes one strange function. Let's see, I think we're going to start here. What about here? Pretty strange.
Excellent. So this is very good in that there's steps in this function. There's all this sort of nonlinearity. And it's a very complex function. If you were trying to approximate this function with a standard linear model, it's possible, but it would take a lot of work. You would actually have to do tons of feature engineering on this x to be able to follow all of this path when you train your model. But what would a decision tree do? A decision tree would look at this and say, hey, I could split right here on this data, and all of the data on this side is going to be a lot different than all of the data on this side. What's more, so this could be the first split. Split 1, right here. This is 0, 1. Okay, so that's the first one. It could split again over here. It could say, hey, it's really easy to see how to split this data so that one side is very different than the other. And so it could split the data right here. And this would be the second split point. Again, it would look and say, oh, we know how to split the data even further on this side. By splitting the data here, this part of the line, the average value of this part of the line, is very different than the average value of this part of the line. And so this is a great split point for it. And then looking more, well, maybe we split this in half here, and maybe this right here would have another split. And this is, again, this is an incredibly, oops, did that a little too fast there. Okay, this is an incredibly simple decision tree right here. Only a very few splits. But what we could see by doing these splits here, this is how it would look on the decision tree surface. Like that. By looking at just in this segment and taking the average values of all of the lines in this segment, we get something like this. I'm going to make a really thick line so you can differentiate it from my lines down there. By taking the average value of all of the dots or the line in this segment, we get this. By taking the average value of the line in this segment, we get something there. And so on here, I'm going to do one more split because I bet this could efficiently be split one more time. Line here, the average value here, and then the average value here. So your final function looks like this, with very few splits. This is an incredibly simple decision tree. And you could see that it follows the path of this very nonlinear, very complex function for you automatically. So that's the power of decision trees, and what we'll see is by combining decision trees with bootstrapping, we'll be able to build random forests, which are incredible.